So today I'm going to talk about why we know that the speed of light in a vacuum is constant. Now, I would like to point out that I'm going to just be talking about why it's constant, and I won't be getting into relativistic effects. I just wanted to point that out in case you were expecting that from the video, so I don't disappoint you. But nevertheless, let's get to it. Alright, so before I get into why the speed of light is constant, I'm going to explain why it's counterintuitive. So, say you're on a train. There you are. And the train is moving at 20 meters per second. You then throw a ball that is moving at 10 meters per second. So, relative to you, the ball is obviously moving at 10 meters per second. Now, you have a friend on a platform that is stationary relative to the Earth, and he measures the speed of the ball and states that it is 30 meters per second. Now, he gets this from the 10 meters per second that you see the ball moving at, and the 20 meters per second that the train is moving at. So combining those two together, he of course gets the 30 meters per second. Now, this is what one would expect. However, say you on the train were to shine a flashlight. Now, if you would then measure the speed of that beam of light, you would get that it is c. Now, I'm going to have c stand in for the speed of light. So essentially, you'd measure the speed of light, and you would figure out that, shockingly, it is the speed of light. So you measure it as c. Now, your friend on the train also measures it as c. And this is not what one would expect. One would expect that the speed of light would be, for your friend at least, would be c plus the 20 meters per second of the train. However, it is not. It is just c. This is not what one would expect. Now, of course, the figuring out that the speed of light was constant was not done by measuring it on a train, but was rather determined from Maxwell's equations. Maxwell was a scientist from the 1800s who worked a lot with electromagnetism. And he developed with a set of equations that describes how electromagnetism works. Now, from those equations, you can come up with a ratio that describes the speed of light. The interesting thing about this ratio is nowhere in it does it have velocity. Now, this indicates that, as I showed with the train example, the relative velocities of the observer or source do not matter, but rather the speed of light is constant for all observers. So it wasn't actually determined from the train, it was determined from Maxwell's equations and the lack of a v variable. But nevertheless, it is still counterintuitive. Now, the fact that light was a supposed constant wasn't overtly concerning to scientists back then. They figured it behaved similar to sound. Sound also travels at a constant velocity for all observers. So, for example, let's say you're standing here, and your friend is standing over here, and you yell a message to your friend. Now, we'll say it's a nice warm day with a constant temperature. So, your message travels at 345 meters per second, which in our case is the speed of sound. Now, let's say you're running towards your friend at 5 meters per second, and your friend is still standing here, and you yell another message to your friend. Now that message would still travel at 345 meters per second. This is because the medium through which sound is traveling, in this case air, does not allow sound to go any faster or slower than the 345 meters per second. So that means that sound is constant relative to the medium through which it travels. Now, due to this, the speed of the sound emitted is 340 meters per second, which is added to the 5 meters per second at which you're running, creating the net total of 345 meters per second. Now, the lower emitted velocity results in a different frequency and a bunch of other stuff, which I'm not going to get into. Now, scientists figured that a similar thing happened with light, in that light, or the lack of a velocity function in Maxwell's equations, just meant that light traveled at a constant velocity relative to the ether, which is what scientists called the proposed medium through which light would travel. And light traveling through the ether essentially worked in the same way at which sound travels through air, in which it travels at a constant velocity relative to the ether, and if you're moving relative to the ether, that just causes the light to have a different frequency, essentially, but then just have a slower emitted speed. So essentially, light behaves similar to sound. Now in step Michelson and Morley, who decided to determine the ether's existence. Now, if light supposedly needs the ether to travel, and light can go almost everywhere, then that means that the ether needs to be almost everywhere. And if the ether is pretty much everywhere, that means that we'd be traveling through the ether right now. And if we were traveling through the ether right now, the ether must be frictionless, because if it had friction, the Earth would automatically travel through the ether, and as it orbits the Sun, if the ether had friction, the Earth would slowly lose energy and eventually crash into the Sun. Since the Earth has obviously not crashed into the Sun, the ether must not have friction. Essentially what I'm trying to get at is that the ether would be very hard to detect. But nevertheless, Michelson and Morley figured out a way to do such. And to explain their method, first we need the Sun and the Earth. Now, it is impossible to determine relative to what the ether is stationary, but ultimately it doesn't matter. So, to keep things easy, we'll say that the ether is stationary to the Sun. This means that the Earth is moving at a velocity v relative to the ether. Now for Michelson and Morley's apparatus. It was essentially a laser which emitted a beam of light, which was split so that some of it would continue on, while some of it was diverted at 90 degrees. Both beams were then deflected by a mirror and were sent back to be picked up by a detector. Now, this detector would determine how long it took the beams of light to complete their journey. And it was very accurate in this. Michelson and Morley also very precisely measured the distance that the beams of light would travel. So, since they have both the distance and the time, Michelson and Morley could rather accurately determine the velocity of the speeds of light. Now, since we're saying that the Earth is moving in this direction with velocity v, that means that the ether is moving in this direction at velocity v relative to the Earth. Now, because this beam going this way is unaffected by the moving Earth, this would give a truly accurate reading of the speed of light. However, since this beam is affected by the Earth moving relative to the ether, this beam is affected by the speed of light, or by the ether, which results in a different speed of light. Now, since it is technically possible that at the exact moment Michelson and Morley performed the experiment, that the ether would be stationary relative to the Earth, and they would thus get the constant speed of light for both beams, they performed it at different times of day and at multiple days of the year. What they found is that in all circumstances, the speed of light was constant. This effectively disproved the idea of the ether and proved that light was a universal constant. So that was my explanation as to why we know that the speed of light is constant. If you'd like to learn more about it, such as the actual apparatus that Michelson and Morley used, I'd encourage you to look that up online. And also, this is the jumping off point for Einstein's theories of relativity. But nevertheless, I hope you enjoyed it, hope you learned something, and see ya!